All forms of jet propulsion rely upon the principle of reaction as described by the 18th century mathematician and natural philosopher Sir Isaac Newton, whose third law of motion was that for every action there is an equal and opposite reaction. It's not the escaping air that moves the balloon forward, but the pressure imbalance within the balloon that makes it move in the direction away from the stem. And by applying Newton's second law of motion, we can calculate that reaction force. Acceleration of a body is directly proportional to the mass of the body, or F equals ma. Bernoulli's theorem relates to the laws governing gas. But what constitutes a gas? A gas may be considered as a collection of molecules in motion, each of which behaves as though it were a perfect elastic body. When a quantity of gas is contained in a closed vessel, the molecules travelling in all directions produce a continuous bombardment on the walls of the vessel, and it's the average force of this bombardment which manifests itself as a pressure of the gas on the walls. Work produced by a gas turbine engine is in proportion to the amount of heat released internally, most of which comes from the burning of fuel, although some heat originates when air is compressed by the compressor. But, as we all know, temperature and heat, although related, are not one and the same. We directly measure the temperature of water or air using an ordinary thermometer. Heat, however, cannot be measured directly, but must be calculated from three known quantities. They are temperature, mass or weight, and specific heat. Let's look at two blocks of iron, one weighing 10 pounds and the other 1,000 pounds. Both are at the same temperature. The larger block, however, has 100 times the heat of the smaller because it has 100 times the mass. We should be aware that both Fahrenheit and Celsius scales are in use in aviation and are often confused. For example, the Fahrenheit scale is used by engineers to calculate and describe engine performance. Temperature indicators on aircraft instrument panels, however, are all read in degrees Celsius or centigrade, which includes the temperature instruments of the aircraft's engines. The successive increases and decreases in velocity practically cancel each other out. Air leaves the compressor and passes to the diffuser, which converts the velocity energy to pressure energy. On leaving the diffuser, the air passes into the combustion chambers. Of the total mass of air passing to the combustion chambers, approximately 25%, known as primary air, enters the flame tubes through the flame tube orifice and is used for combustion. The remainder of the air passes along the outside of the flame tubes, entering through dilution holes in the side of the tubes, and is used for cooling. We better understand the relative performance of different types of turbine when we understand thrust and propulsive efficiency. The force that propels an aircraft is known as thrust, and it is the amount of static thrust a jet engine produces by which it is rated, just as a piston engine aircraft is rated in horsepower. Thrust is a function of the altitude and airspeed of an aircraft and of the engine control setting. It is this thrust force that accelerates the aircraft and balances drag. Because thrust is equal to mass times acceleration, as the density of the atmosphere decreases with an increase in altitude, so does the available thrust. The thrust of a gas turbine engine is directly proportional to the atmospheric density. From this we can interpret that thrust is not just that which comes out of the back of a gas turbine engine. Sadi Carnot, a French engineer, discovered the rule of thermodynamics that states, "The efficiency of converting heat into useful work depends on temperature differences." He might have added, "and the colder the better." If we go looking for the coldest air, we'll find it in the lower stratosphere above 33,000 feet, where the temperature is about minus 55 degrees Celsius. The efficiency of gas turbine engines improves as the difference between the intake temperature and the combustion temperature increases. Axial flow type compressors are better suited to high mass flow, where the air flows parallel to the compressor shaft. Some engine designs incorporate both types of compressors, where an axial flow compressor feeds a centrifugal compressor. Each ring of blades and its associated fixed stator vanes is called a stage, so that the air alternately passes between rotor blades and stator vanes. Without the stators, centrifugal action causes the air to flow radially outwards between the vanes. At the same time, the impeller rotation causes tangential flow. Pressure of the outflow air rises because of the diverging passages between the vanes. Each stage has a ring of fixed guide vanes and a row of moving blades or turbine rotors. The number of stages depends on whether the engine has one shaft or two, and on the amount of power required from the gas flow, as well as a number of other factors. In modern engine design, the trend is towards more rather than less stages in order to reduce the stage loading. Turbine blades extract energy from the gas stream in two ways: by impulse and reaction. Normally, turbine blades combine both impulse and reaction principles.